Hey everyone, and welcome to this explainer. Okay, we are jumping right into something I absolutely love today. We're setting out to demystify one of the single most powerful analytical tools in a chemist's arsenal, carbon-13 nuclear magnetic resonance, or 13C NMR. If you've ever stared at a massive, complex organic molecule and wondered, how on earth do scientists map out its exact carbon skeleton without actually seeing it, well, you are definitely in the right place. We're going to break down this molecular map together, step by step.
But before we get into the nitty-gritty details, I want you to just think about this massive detective problem for a second. Carbon is literally the foundational building block of organic chemistry, right? Yet the standard isotope of carbon, carbon-12, which makes up about 99% of all carbon in nature, is completely invisible to an NMR spectrometer. It has a nuclear spin of 0, which just means it doesn't interact with the magnetic fields we use to probe these molecules. So how do you map out a backbone when almost the entire thing is practically a ghost to your instruments?
Well, the answer lies in the ultimate underdog of the elemental world, carbon-13. A mere 1.08% of all carbon atoms out there in nature are the carbon-13 isotope. It is incredibly rare. But, unlike its abundant sibling, carbon-13 has a nuclear spin of 1/2, making it NMR active. This tiny, tiny fraction of a percent is our one and only window into the carbon backbone of a molecule.
So, here's our mapmaker's guide for today's explainer. First, we'll meet the carbon-13 nucleus. Then, we'll map out the chemical shift landscape, learn how to read correlation charts, and finally, look at what actually drives the shifts.
Let's start with Section 1, meet the carbon-13 nucleus. So looking at these two isotopes, the contrast is pretty wild. Carbon-12 is everywhere, but it's totally useless to us in NMR because its nuclear spin quantum number is just 0. No spin means no magnetic moment. But our rare friend, carbon-13, has an odd mass, which actually grants it a quantized spin angular momentum of 1/2. When you put this nucleus in a really strong magnetic field, it can adopt one of two spin states. It'll either align with the field or oppose it. And it's the energy difference between those two specific states that we use to generate our signal.
Now, relying on an isotope this rare definitely throws some major hurdles our way. First off, because of its low natural abundance and a lower gyromagnetic ratio, carbon-13 signals are roughly 6,000 times weaker than the proton signals you're probably used to seeing in standard hydrogen NMR. 6,000 times! Plus, the chances of finding two carbon-13 atoms right next to each other in the same exact molecule, practically 0. No single molecule is giving you a complete spectrum. To actually overcome this, modern spectrometers rely heavily on Fourier transform instrumentation, or FTNMR. This amazing tech lets chemists accumulate and add together hundreds, sometimes thousands of individual scans just to pull that incredibly weak carbon signal out of the background noise.
Moving right along to Section 2, the chemical shift landscape. If you've spent any time looking at proton NMR, you know it operates on a really tight scale, usually between 0 and 12 parts per million, or ppm. And because it's so squeezed together, you get these messy, overlapping peaks all the time. But carbon-13? Its scale is massive. It spans from 0 all the way to over 220 ppm. And here's the absolute best part. Because of this huge range, nearly every non-equivalent carbon atom in an organic molecule gets its own distinct non-overlapping peak. It is just incredibly clean to read.
We can actually chop this huge 220 ppm landscape up into 4 really distinct, friendly little neighborhoods. Starting all the way on the right side of the spectrum, at the lowest ppm values, we find our saturated sp3 hybridized carbons sitting pretty comfortably between 8 and 60 ppm. Now, as we move downfield, which means leftward, to the higher numbers, we hit the 40 to 80 ppm zone. This is where electronegative atoms start tugging on those carbons. Go a bit further left, between 100 and 175 ppm, and we find our unsaturated sp2 carbons and aromatic rings. And finally, parked way down at the extreme downfield end, between 155 and 220 ppm, are the carbonyl groups. They're shifted out the absolute furthest because they're both sp2 hybridized and directly attached to an electronegative oxygen.
Okay, on to Section 3, reading correlation charts.
When you look at a real carbon-13 NMR spectrum like this one, the first thing you'll notice is just how remarkably crisp it is. Instead of those complex, clustered multiplets you have to untangle in proton NMR, we just have this nice, neat series of sharp, isolated spikes, or singlets. It makes counting the number of unique carbon environments in your molecule so straightforward. But you might be wondering, why are there no splitting patterns here?
The secret behind that beautiful simplicity is a technique called proton decoupling. The vast majority of carbon-13 spectra you'll ever see are obtained this way. Essentially, the instrument bombards the sample with a broad frequency that perfectly obliterates all the spin interactions between the attached hydrogens and the carbon-13 nuclei. Now, the trade-off here is that we do lose the information about exactly how many hydrogens are attached to each carbon, but what we get in return is this beautifully simplified map made entirely of singlet peaks, completely avoiding the nightmare of overlapping multiplets. It's a pretty good deal.
Now, when you're looking at one of these decoupled charts, there's a landmark you're going to spot almost every single time. It's a tight, three-peak pattern, a triplet, centered exactly at 77 ppm. This is your solvent, which is usually deuterated chloroform, or CdCl3. Now, it's a triplet not because of hydrogen coupling, but actually because the carbon is coupling to the deuterium atom, which follows a slightly different set of splitting rules. Spectroscopists literally use this 77 ppm landmark as a super reliable internal reference point just to orient themselves on the map.
Which brings us to our final section, what drives the shifts?
So, there are three main physical phenomena driving these chemical shifts: electronegativity, hybridization, and anisotropy. If you studied proton NMR before, these are going to sound very familiar, because they affect carbon-13 shifts in pretty much the exact same way. The big difference here, the effect is roughly 20 times larger in carbon NMR. This 20x rule happens because the substituent atoms are directly attached to the carbon being observed, so it's a one-bond interaction, rather than acting through two bonds to try and reach a hydrogen atom.
Let's really zoom in on the most common driver, the electronegativity effect, which leads to this concept called de-shielding. I like to think of the electron cloud around a nucleus as a nice protective magnetic blanket. When an electronegative element like oxygen or halogen attaches to the carbon, it acts like a blanket thief. It literally pulls that electron density away, leaving the poor carbon nucleus exposed to the full force of the spectrometer's applied magnetic field. And because it's feeling a much stronger field, its resonant frequency increases, shifting its peak way further downfield, to the left side of our map. Let's trace how this electronegativity effect actually plays out step by step in a molecule. When that electronegative atom attaches, the alpha carbon, the one directly attached, experiences a huge downfield shift because the effect is happening right through a single bond. The neighboring beta carbon? It also shifts slightly downfield. But here is where nature throws us a real curveball. It usually leads to a small upfield shift for the gamma carbon, the one that's 3 bonds away. I know, it seems completely contrary to expectations, right? But that's exactly why you can't just guess these values in your head. It really proves the absolute necessity of keeping detailed 13C correlation tables handy to predict these chemical shifts accurately. So, that brings us to the ultimate question. By taking advantage of that tiny 1.08% of carbon that is NMR active, decoupling the protons to clear the clutter, and understanding how de-shielding moves our peaks around, we've built a brilliantly clean map. We know exactly how many unique carbon environments there are and roughly what functional groups they belong to. But wait, since we decoupled the protons to get this clean map, we just threw away our connectivity data. So how on earth do we figure out exactly which hydrogens are connected to which carbons? Well, for that, you have to literally layer the 1H and 113C maps on top of each other using a 2D technique like heat core. But hey, that is a massive, fascinating puzzle for another explainer. Thank you so much for joining me today, and keep exploring the data.